All right, we're about to tackle a question that on the surface sounds super simple, like first grade science class simple. But trust me, the answer, well, it pushes the very boundaries of what we think of as reality.
So, what is a particle? I mean, think about it. Everything, absolutely everything, you, me, the device you're watching this on, the most distant star you can imagine, it's all made of particles. But here's the crazy part. Trying to pin down what a particle actually is, well, that's turned out to be one of the biggest, most mind-bending challenges in all of physics.
You know, for a long, long time, we thought we had this figured out. But oh man, has our understanding been completely turned on its head. It turns out that at the very heart of all this, the basic stuff of the universe, there's this incredible mystery that we are still trying to piece together. And look, it's not just us scratching our heads. The top physicists in the world, they'll tell you straight up, this is the frontier. I love this quote from Zhao Wen at MIT. He's basically saying that when we call something fundamental, it's really just a way of saying, don't ask, I don't know the answer. How great is that? Fundamental isn't the final word. It's just the beginning of the real adventure.
Okay, so to really get into this investigation, let's peel back the first layer. We'll start with the most intuitive, kind of common sense idea of what a particle is. The simple, classical picture. This is probably what you learned in school, right? A particle is just a teeny tiny, dimensionless dot. You know, an electron, a quark, a photon, they're just these little points in space with zero size and no internal bits and pieces. Seems simple enough?
Yeah, well, not so fast. Because right away, you hit a massive problem. How can something with literally zero size have mass? How can a point with no dimensions whatsoever carry an electric charge? Think about it. This one simple question just completely unravels that whole definition. The idea of a point-like object, it just doesn't work. So that means we've got to peel back that first layer. And this is where things get really weird and really cool. Welcome to the world of quantum mechanics. See, in the quantum world, a particle isn't a fixed little point, not at all. It's what's called a wave function, which is basically this ghostly, spread-out cloud of probabilities. So before you measure it, an electron isn't here or there, it's everywhere it could possibly be, all at the same time. Wild, right? But then, something incredible happens. The instant you try to measure it, the second you look, that entire cloud of possibility just collapses. It snaps down to a single point, and your detector goes click. This whole thing, the collapse of the wave function, is one of the biggest, deepest mysteries in all of quantum mechanics. We still don't really get it. But wait, it gets deeper. Even this idea of a wave function isn't the final story. To really make quantum mechanics play nicely with Einstein's relativity, physicists had to come up with an even more fundamental idea, and that is quantum field theory, or QFT for short. So according to QFT, the most fundamental things in the universe aren't particles at all. They're fields. Just try to picture it. All of space is filled with these invisible fields, an electron field, a photon field, one for every single type of particle. And what we think of as a particle, it's really just a tiny localized vibration, a little ripple, or what physicists call an excitation in that field. Okay, let's recap. We've gone from a point to a wave to a ripple in a field. Now, for the next layer, we're going to pretty much strip away the physical picture altogether. This is where a particle gets defined by pure, elegant mathematics. All right, now, if you ever want to sound super smart at a party and you ask a physicist, what is a particle? They might hit you with this one. It sounds like a total mouthful, I know, but I promise the basic idea behind it is actually pretty intuitive. It all comes down to one beautiful concept: symmetry. So what in the world is a symmetry group? Let's make it simple. Think of an equilateral triangle. You can rotate it by 120 degrees and boom, it looks exactly the same. That rotation, that's a symmetry. A group is just the complete collection of all the things you can do to an object, all the transformations that leave it looking identical. Okay, now take that idea and apply it to, well, space-time itself. The Poincare group is basically the master list of all the ways you can move or rotate something, shifting it left and right, spinning it around, even pushing it forward in time without changing the fundamental laws of physics. And here's the mind-blowing part. In this definition, a particle is the simplest mathematical thingy that behaves perfectly under all these cosmic symmetries. Its properties like mass and spin, they aren't random. They fall right out of the fundamental symmetries of our universe. It's beautiful, really.
And that brings us right to the absolute cutting edge. This is where physicists are going even deeper, asking questions about the nature of space-time itself, all in the quest to finally figure out what a particle really is.
Out here on the frontier, you've got a couple of big ideas duking it out. One is called it from qubit, and it's exactly what it sounds like. The idea that the universe isn't made of stuff, but of information. You know, the qubits you hear about in quantum computing. In this picture, space-time and all the particles in it are like a hologram, projected from some deeper reality made of information. Then you've got another camp, the amplitudologists, who say, forget fields. They're just a convenient story we tell ourselves. They think we should only focus on the pure math of how particles interact. Because when you do that, these unbelievably simple, beautiful geometric patterns just pop out. Patterns that were totally hidden before. So, after all that, after this whole journey from points to waves to fields to pure math, what's the final answer? What is a particle? Well, here's the beautiful part. The question is still completely wide open.
You ask some physicists like Dimitri Nanopoulos, and they'll tell you the real secret is in that moment of measurement, that instant when a cloud of possibility snaps into a hard reality. Then you've got others, like Nima Arkani Hamed, who are way more pragmatic. For him, a particle is just what makes our detectors go click. Simple as that. Everything else, it's just scaffolding we build around that one observable fact. And then you have brilliant minds like Zhaogang Wen, who kind of weaves these ideas together. He sees particles as quantized waves, but those waves are actually just deformations, ripples in this vast ocean of quantum information.
So think about where we've been. From a simple point to a ghostly wave to a ripple in a field, then to a purely mathematical form, and now maybe even a hologram made of pure information. It's the search itself, you see, that's driving our whole understanding of reality forward.
And maybe, in the end, the most honest and, to me, the most exciting answer comes from Netta Engelhardt at MIT. The short answer is, we don't know. And that's not a sign of failure. Not at all. That's the very engine that drives science.
Which leaves us with one last, really mind-bending thought to chew on. As we keep digging for the true definition of a particle, what if we find out that the most fundamental thing in our universe isn't a thing at all? What if it's an idea? Or a piece of information? Or maybe just a pure mathematical relationship? What would that mean for, well, for everything?